The fracture of a metal part or component is probably the most serious type of failure. But a fracture is only one of several different types of failure. In addition to fracture, the major failures are due to wear, corrosion, and distortion. Generally, wear is not as serious as fracture. Wear, however, is of tremendous economic importance and can lead to fracture. Corrosion is very similar to wear in many respects. It is a type of deterioration, usually at the surface of a component, and corrosion can lead to wear. It can also lead to fracture. Distortion is generally not as serious as the other types of failure. However, when parts are permanently distorted or deformed, they cannot perform their intended functions. And this is considered failure, even though the part, machine, or equipment may continue to operate with what essentially is a faulty component. Though fracture, wear, corrosion, and distortion are generally considered the major types of failure, it must not be assumed that each acts independently of the others. Indeed, one of the challenges in the field of failure analysis is to recognize the wide variety of combinations and interactions of fracture, wear, corrosion, and distortion. For example, elastic deformation occurs until the elastic limit of a metal is exceeded. At this point, plastic deformation occurs, which is essentially permanent distortion. The final result may be a single overload fracture. Corrosion fatigue combines the long-term effects of corrosion with those of fatigue, resulting in a particularly serious type of fracture. Propeller shafts of ships are very susceptible to corrosion fatigue. Corrosive wear is a major source of deterioration in many types of machinery, particularly internal combustion engines. Both wear and corrosion can reduce section thickness until fracture occurs. In the real world, an infinite number of interactions take place constantly between alloys, parts, and equipment that are subjected to various chemical and thermal environments, applied stresses, and residual stresses. Metals are fatigued by repetitive loading, altered by heat treatment, and subjected to forces beyond their physical capacities. Consequently, the fundamental sources of failure include many aspects of design, material selection, material imperfections, fabrication and processing, reworking, assembly, inspection, testing, storage, and even shipment, service conditions, maintenance, unanticipated exposure to overload, elevated temperatures, and mechanical or chemical damage in service. Because of the many combinations and interactions that lead to failure, unraveling the complexities of intertwined causes is challenging work for the failure analyst. It is, however, quite simple to determine whether or not a part has failed. In general, a part or assembly is considered to have failed when any of the following conditions exist. When the part or assembly becomes completely inoperable. When the part is still operable but no longer able to perform its intended function satisfactorily. Or when serious deterioration has made the part unreliable or unsafe for continued use. The study of failure and stress should begin with distortion. Distortion is often a warning of overload preceding fracture. Distortion is also easy to recognize by cursory observation with the unaided eye. Permanent distortion is the least serious mode of failure. It involves not only the metal part itself, but also its design and usage. Distortion can be caused by any of four different mechanisms. Yielding. The applied stress exceeds the elastic limit of the metal. Buckling. The collapse of a part, usually a long, slender part subjected to an axial compressive force. Creep. Time-dependent strain, causing metal to gradually change shape and size. Creep is generally associated with high-temperature service. It will be discussed in another program. And residual stress, the forces locked inside the metal, subjecting the part or assembly to internal stress. Each of these failure and stress mechanisms is completely different in origin. They are similar only in that each causes distortion. Yielding. Yielding is permanent distortion. A part yields or distorts permanently when the stress on the part exceeds the elastic limit of the metal. When a spring or other part changes shape permanently after the application and removal of a load, the elastic limit of the metal has obviously been exceeded. Yet yielding is a very necessary ingredient in many manufacturing processes, such as drawing, bending, and forming operations. To prevent yielding in service, however, it might seem logical to increase the yield strength of the part by heat treatment or using some other metal. Well, sometimes this can be done, but if a metal already has a high yield strength, increasing the strength even more may lead to a more serious type of failure, brittle fracture. Yield strength might also be increased by increasing the section size. We beef it up to reduce the stress. Well, this can be done in some cases, but this can also affect the function. Increasing the section of a spring, for instance, makes a stiffer spring and changes its spring rate. Beefing it up can also lead to space, weight, and clearance problems. Sometimes it may be feasible to change the design of a part, adding flanges or corrugations or braces to make it stronger and reduce the stress. Again, this increases the stiffness, which may be acceptable in some cases, but not in others. We can also avoid yielding by reducing the load on the part. Once again, this may not be feasible. Buckling. The distortion caused by buckling is defined as compressive instability. Components subjected to compressive stresses, especially long, slender columns or tubes under axial compressive stress, can distort by buckling, causing entire structures to collapse. Thin-walled tubes buckle or wrinkle on the concave side when bent or subjected to high torsional stress. Since the modulus of elasticity of a metal at any given temperature cannot be changed, its buckling load cannot be changed by increasing the strength or hardness of the metal. Long columns supporting a structure must be straight in order to attain the maximum buckling load, and the ratio of length to diameter must be relatively low. In essence, buckling is a design problem, not metallurgical. Creep. Distortion caused by creep is somewhat similar to the problem of yielding. Creep is gradual distortion, generally occurring over long periods of time at relatively high temperatures. The bolts holding the hotter parts of an engine together, the exhaust manifold for instance, may gradually loosen over a period of time and need retightening. The loosening may be caused by vibration, but sometimes the bolts absorb heat from the engine and gradually stretch. The creep distortion continues after each retightening until the threads become too distorted to hold. Residual stress. The three mechanisms causing distortion in metal, yielding, buckling, and creep, are fairly obvious and easy to understand. The fourth mechanism, residual stress, is very often overlooked because it is not obvious. Yet the residual or internal stresses within a part or assembly are just as important as the applied or external stresses. Understanding the applied or external stresses can be so intuitive that a skilled investigator can automatically visualize them in almost any situation. Applied stresses can be visualized qualitatively. They can be calculated by equations found in strength of materials texts, and they can be measured by strain gauge techniques. Residual stresses, however, are not only difficult to measure, they are nearly impossible to calculate as well. But don't be misled by thinking that residual stresses are necessarily detrimental to the life of a part. When the residual stresses are tensile and at the surface, they are generally detrimental. But surface compressive residual stresses are extremely helpful and beneficial to many parts undergoing applied torsional or bending stresses. In fact, several types of metalworking processes exist solely to impart compressive residual stresses into surfaces. More about this later in the program. In reality, most fractures of moderate to high strength metals are caused by a combination of both residual and applied stress. The resultant stress on any part or component is the algebraic sum of both the applied and residual stress. Either type of stress, applied or residual, can be positive or negative. The tensile stress is positive, the compressive, negative. The resultant stress can be caused by either 100% applied stress, 100% residual stress, or any combination of applied and residual stress. Applied stress. Most fractures, the most serious type of failure, are caused by applied tensile stresses. In brittle materials, they may also be caused by compressive stresses. For the failure analyst, visualizing the applied stress can be fairly simple and automatic. For example, if a straight flat bar is loaded at the ends with a fulcrum at the center, it seems almost obvious that fracture will occur somewhere on the upper surface, somewhere on the convex side of the bar in tension. The lower surface is squeezed in compression and becomes concave. It is the relationship between the applied stress and the inherent strength of the material that determines the location where any type of fracture will originate. This is another way of saying that a chain is only as strong as its weakest link. But in actual parts, fracture will generally originate wherever the local stress first exceeds the local strength. Consequently, metal parts are frequently and deliberately made with regions of higher and lower strength by heat treating to form a surface that is stronger than the interior. The two most popular processes are carburizing and nitriding. With this kind of treatment, fracture will not originate in the weaker interior unless the stress at that location exceeds the strength at that point. More about this later. For now, it may be more important to visualize the distribution of stresses through the material that leads to fracture. To understand and visualize the distribution of stresses applied to a part, we must first determine the type of loading on the part. A part can be loaded in tension, compression, torsion, bending, gross macroscopic shear, or any combination of these. In tension, the member is simply pulled. The applied stress is uniform across the section, and the force is considered positive because the metal tends to become longer. On a graph, the tensile stress is depicted in a positive direction. When the applied stress is compressive, an action that tends to make the member shorter, the force is considered negative. Graphically, compressive force is shown in the negative direction. The stress, positive or negative, tensile or compressive, is uniform across the section of the member. This means that a fracture can originate anywhere in the section. Fracture can occur near the center of the bar, at the surface, or anywhere in between. But suppose a notch is cut into the surface of the bar. The tensile stress will no longer be uniform across the entire section, but will be concentrated at the tip of the notch. The stress concentration can reach very high values depending on the sharpness of the notch. Any type of internal cavity within the section will also cause a stress concentration. The cavity can be a hole drilled through the part, an internal inclusion, or internal porosity of any kind. The degree of stress increase at the site of the stress concentration depends on the sharpness and orientation of the internal notch at that location. Under a compressive force, the elastic stress distribution is exactly the same as in tension, but in the opposite direction. Ductile metals do not fracture in compression, simply because the metal is being squeezed, not pulled apart. The metal yields or bulges rather than fractures. Yielding is the normal mode of failure in ductile metals under compressive stress. In brittle metals, however, a single load fracture can occur parallel to the direction of the compressive stress, but this is caused by the circumferential tension stress perpendicular to the compression stress. In both ductile and brittle metals, the compressive stress can be concentrated at the tips of notches or at internal cavities, and these stress concentrations will be in the negative direction because of the compressive loading. Torsion is a twisting load. Twisting a shaft or shaft-like part imparts a torsional stress system that is completely different from the tension and compression systems. The torsional stress varies across the section of the part. Maximum at the surface, zero at the center. The center of the part, where the torsional stress is zero, is called the neutral axis. When a part is subjected to a torsional stress, the fracture will normally originate at the surface, where the stress is maximum. Fractures cannot originate deep within the part simply because the stress decreases to zero at the neutral axis. When a transverse hole is added to the shaft, creating a stress concentration, the stresses increase greatly at the edges of the hole. Maximum stresses occur at 45 degrees to the axis of the shaft. Bending creates a tensile and a compressive stress within the part. The top surface of the part will be under a positive or tensile stress, while the undersurface will be under negative compressive stress. Consequently, the stress runs from maximum tensile stress at the top surface to zero at the neutral axis and to a maximum negative or compression at the bottom surface. Once again, these stresses, both tensile and compressive, can be increased by a stress concentration at either or both surfaces of the part. Macroscopic shear is sometimes called direct shear. Shear itself means sliding, and a direct shearing action involves two sharp edges sliding together to cut a third material. The shearing action is like a pair of scissors or shears cutting a piece of paper. The paper is cut along a shear plane. Double shear involves three sliding or shearing members which cut a fourth member. The action is similar to that of a clevis joint under load across a pin, rivet, or bolt. The cross member is cut along two shear planes rather than just one plane as in a single shear. Summary: the major failures are due to fracture, wear, corrosion, and distortion. Wear can lead to fracture. Corrosion can lead to fracture and wear. Distortion can deform parts so that they cannot perform their intended function. Plastic deformation is essentially permanent distortion. Distortion can be caused by yielding, buckling, creep, and residual stress. Fracture can originate wherever the local stress first exceeds the local strength. Parts can be loaded in tension, compression, torsion, bending, gross macroscopic shear, or any combination of these. Stress systems. The stress systems that can exist within a single part or component can be extremely complex, making it very difficult for even an experienced failure analyst to unravel. All three systems, tension, torsion, and compression, can exist together, each acting on one another. This interaction of stresses can confuse the evidence. One way to simplify the study of stress systems is by the examination of free body diagrams. A basic free body diagram pictures all three stress systems as they might appear in a cylindrical part. In tension, the shaft is pulled at both ends. The free body diagram is arranged with the tensile arrows in the direction of the tensile stress. As the tensile stress is applied, the part tends to elongate. The part also tends to contract on the sides, creating a compressive stress component inward to the center of the part. The direction of this compressive stress is shown by the compression arrows, perpendicular to the direction of the tensile stress. The free body diagram shows both these stresses, the tensile stress and the compressive stress, applied to the cylinder. By turning the diagram 90 degrees inside the cylinder, the arrows now show a compressive stress applied at the ends of the cylinder. As the compressive stress is applied, the cylinder tends to bulge outward from the resulting tensile stress. The tensile stress component is shown perpendicular to the compressive stress. The direction of shear stresses can also be visualized in the free body diagram. Shear occurs at a 45-degree angle to the axial tensile stress and the transverse compressive stress. There are two sets of shear stresses, each perpendicular to the other, diagonally between the normal stress directions. Rotating the free body diagram 45 degrees inside the cylinder, lines up the shear arrows in the direction of shear stresses as they might be applied to a cylinder twisted in torsion. If the cylinder is twisted at the top and bottom, the stress rotates diagonally through the section. The normal tensile stress is still perpendicular to the normal compressive stress, and both tension and compression are 45 degrees to the axis of the cylinder. The shear stresses are longitudinal and transverse. Using this single free body diagram, we can picture the entire stress system that creates a fracture, and how these three different stresses interact with each other, causing metals to fracture in predictable ways. A fourth failure mode, fracture by fatigue, is also encountered. Fatigue is unique because it is a composite of two types of single load fracture. The repetitive stress applications in the elastic range can cause fatigue cracking in the shear stress direction, which subsequently changes to the brittle fracture direction. Fatigue will be covered in another program. For now, let's see how ductile and brittle metals react under these three stress systems: tension, torsion, and compression. In a ductile metal stressed in tension, a fracture develops with an elastic extension and then a plastic extension. As the extension increases, necking develops as the compressive stress increases and the metal nears fracture. In the final stages of the fracture process, millions of tiny internal microvoids, or cavities, develop in the necking region. These microvoids join together, coalesce, and form a rough, jagged fracture surface. The process is known as microvoid coalescence. The joining cavities progress outward in a generally transverse direction. Before the fracture reaches the surface, however, it suddenly changes direction from transverse to a slant of about 45 degrees. This slant portion of the fracture is the familiar shear lip that forms the dull and fibrous appearing cup and cone fracture typical of tensile fractures in ductile metals. In brittle metals stressed in pure tension, the fracture is essentially perpendicular to the tensile stress, straight across the section. There is little or no plastic deformation before fracture occurs. Truly brittle materials cannot deform plastically, as ductile or moderately ductile materials can. The characteristic appearance of fresh fractures in brittle metals is usually bright and sparkling. Ductile metals in pure compression do not fracture. A truly ductile metal will simply bulge laterally as it becomes shorter. A brittle metal in pure compression will, as always, fracture perpendicular to the maximum tensile stress component. Brittle materials such as glass, chalk, rock, and very brittle metals split or shatter longitudinally in many slivers when loaded in compression. The increase in diameter and circumference with the increase in circumferential and radial tensile stress components causes the brittle material to shatter longitudinally. Shear stresses are longitudinal and transverse. Each pair of stress components remains mutually perpendicular to each other. In a ductile metal subjected to torsion, fracture begins with elastic, then plastic deformation. Shear stresses exceed the shear strength of the metal. The deformation caused by torsion may not be obvious unless there were previous longitudinal reference marks on the shaft prior to twisting. Twisting deformation can be made visible in wrought metals by chemical macro-etching, revealing the originally longitudinal grain flow. Spiral lines in the metal show the deformation. With pure torsional deformation, the length and diameter do not change. To understand why, we can imagine that the shaft consists of an infinite number of infinitely thin discs. When the ends of this pack of discs are twisted, each disc slips a very small amount with respect to its neighboring discs. But the diameter of each disc does not change, nor is there any force to change the length. As the torsional stress increases, the slippage and deformation continues. Eventually, fracture will occur on one of the transverse shear planes. This plane is essentially the interface between two adjacent discs. Deformation also occurs on the longitudinal shear planes, but this normally does not cause single load fracture unless the material is extremely weak in the transverse direction. Wood, for instance, has a low splitting strength parallel to the fibers. When a metal fractures from pure torsion, the fracture originates at the surface. The final rupture occurs at the center of the shaft. If a bending stress is superimposed on the part as well, the final rupture will be offset toward one side. A brittle material in pure torsion fractures perpendicular to the tensile stress component, exactly as it does in tension. But the tensile stress component is now at 45 degrees to the axis of the shaft. Thus, the fracture is spiral, providing the metal is brittle throughout its section. Summary: stress systems and the free body diagram. The free body diagram pictures three stress systems interacting within a part: tension, torsion, and compression. Tensile stress is perpendicular to compressive stress. Shear stress occurs at a 45-degree angle to the axial tensile stress and the transverse compressive stress. Ductile metals in tension fracture by microvoid coalescence. Brittle metals in tension fracture with little or no plastic deformation, straight across the section. Ductile metals in compression do not fracture. Brittle metals in compression fracture perpendicular to the maximum tensile stress component. Ductile metals in torsion deform plastically, then fracture on a transverse shear plane. Brittle metals in torsion fracture perpendicular to the tensile stress component, 45 degrees to the axis of the shaft. Residual stress. The havoc caused by residual stresses goes by many names: grinding cracks, heat checking, quench cracking, weld cracking, thermal fatigue, hot tears, and others. On the other hand, residual stresses in metals can help fracture-prone parts to survive, or at least to survive much longer. A number of extremely useful industrial processes are intended to impart beneficial residual stress patterns in a variety of parts. A large number of highly stressed parts, particularly those subject to fatigue fracture and stress corrosion cracking, are routinely processed by shot peening, ballizing, auto-frottage, surface rolling, and other treatments to impart favorable residual stress patterns in them. To help visualize the residual stresses within a metal part or assembly of parts, we can think of them as springs. A tension spring can represent a tensile residual stress. When loaded in tension, the spring is stretched like a rubber band. A compression spring, representing a compressive residual stress, is compressed like a rubber pad. In this particular model, with the two types of springs between two blocks, a balanced, stable stress system can be created by adding another compressive spring. Now the assembly of parts, a visual model of internal stresses, is balanced and stable. Two compression springs hold the blocks apart. One tension spring pulls them together. If we visualize this model of one tension spring on the inside and two compression springs on the outside as a cylinder or rod, the balanced stress system within the cylinder might look like this. Remember, tension is positive. Compression is negative. Conversely, we could build a similar model with a compression spring in the middle and two tension springs on the outside. Again, the system is balanced, and the two blocks are kept apart by the compression spring and held together by the balancing stress of two tension springs. Each assembly is a stable system, balanced within itself. If any part is removed, the entire system will collapse. The force in each direction is balanced by an equal and opposite force, a corollary to Newton's third law of motion. Each part is stressed. The tension springs are stretched longer than their free length, and the compression springs are squeezed shorter than their free length. Each tension spring is trying to become shorter, while each compression spring is trying to become longer. If the length of any spring is changed, the assembly would change shape, The system would distort to attain a new stable equilibrium or balance. With these spring models, we can visualize actual parts and the residual stresses within metals. Suppose we have a bar with a longitudinal residual stress system of compressive external and tensile internal stresses. If a hole is drilled through the length of the bar, the internal tensile stress will be relieved. To balance the system, the external compressive stresses will be permitted to relax. As the compression stresses relax, the bar will get longer. Suppose we take a similar bar with the same stress system. We machine the exterior to a considerable depth from the surface. With machining, the external compressive stress will be relieved, permitting the internal tensile stress to relax toward its free length. Relaxing the tensile stress permits the bar to become shorter. We can think of similar stress systems as springs in flat plates. Removing a residual stress layer from the surface of a flat plate by machining would cause the plate to bow. The direction of the bow would depend on the type of stress system being considered. The very first measurements of residual stresses were done on a macroscopic scale. That is, measurements of a part were taken, metal was removed from the specimens by machining, and the parts were measured again to determine the amount of distortion. The residual stress that had been in the metal removed was calculated by various methods. This is the dissection technique for the measurement of residual stresses. For many years, X-ray diffraction techniques have been the most popular method of measuring residual stresses. The techniques are based on measurements of lattice strains. The strains cause changes in the spacing between crystallographic lattice planes. The directions of the residual stresses within a part are considerably more complex than a simple spring analogy might indicate. Residual stress systems are always three-dimensional. For example, in a cylindrical part, the residual stresses can be visualized in the longitudinal direction, as shown in the spring analogy, and in the circumferential direction, and in the radial direction as well. In a flat plate, the stresses are in the longitudinal direction, width direction, and the thickness direction. Fortunately, we can ignore one of these directions in many parts because it may be a non-critical direction. Since residual stresses and their directions are so important in failure analysis, let's look at several other assemblies of parts and how they can be considered to have residual stresses. A bicycle wheel is a very light, strong, and carefully designed structure. The wire spokes, assumed here to be radial, are stressed in tension, pulling the rim inward toward compression. At the same time, the spokes pull the tubular hub outward in tension. The significant stresses in this system are in the circumferential and radial directions. The longitudinal or axial stress is negligible and can be ignored. A great many factors create and change residual stresses in metals. These factors affecting the residual stress patterns include thermal, metallurgical, mechanical, and chemical. The thermal factors affecting residual stress are extremely important in metalworking and joining processes. The basic problem with welding and other methods involving localized heating is that metals generally expand when heated and contract when cooled. If they are free to expand and contract without restraint, residual stresses would not be generated. But if both heat and restraint are present, residual stresses are formed. This is what happens in welding. The metal is locally heated and restrained by the metal next to it that remains cool and strong. The mechanical properties of metal are also important to the formation of thermal residual stresses. As the temperature increases, both the tensile and compressive yield strengths decrease. As the temperature increases, the slope of the elastic portion of the curve decreases, thus reducing the modulus of elasticity. In metalworking, we commonly take advantage of this decrease in the modulus of elasticity. At elevated temperatures, metals are weaker but more ductile. This is why metals are heated for forging and other hot forming processes. Another aspect of thermal residual stresses that should be kept in mind is the distortion that can occur in a part with heating. For instance, if the upper part of the metal is suddenly heated, without significant transfer of heat to the lower section, the part can bow. The heated surface tends to expand, but is restrained by the cooler, stronger metal below the surface. At that moment, compressive stresses are formed on the convex upper surface. As the surface cools, the part bows. This is very common during welding and heat treating. Residual stresses by metallurgical factors occur primarily in the martensitic transformation of steel. When steel transforms from austenite to martensite during cooling, the martensite expands about 3 to 4% by volume, depending on the carbon and alloy contents. This expansion causes compressive residual stresses in the transformed region of the part, if there are other regions that did not transform or transformed earlier, depending upon the hardenability of the steel. The principle of metallurgical residual stresses in steel is this: the metal that hardens last is in residual compression. Another complication in the austenite to martensite transformation is that martensitic expansion can occur at the same time a thermal contraction is taking place during rapid cooling. In heat treating, this results in distortion and possible quench cracking. The mechanical factors affecting residual stress include machining, grinding, and cold forming, and mechanical pre-stressing processes, such as shot peening, surface rolling, and ballizing. The surface performance of parts made of metal can be improved tremendously by mechanically induced residual stresses. For best fatigue performance in most cases, compressive residual stresses are desirable on the surface. The basic principles for mechanical residual stresses are: tensile yielding under load results in residual compression when the load is removed, and the reverse. Compressive yielding under load results in residual tension when the load is removed. A simple visualization of residual stress can be described by hardness testing, where a very hard ball is pressed into a softer metal surface. When the ball is at its maximum depth, it stretches the originally flat metal surface into a shape similar to an inverted dome. The original surface is now stretched in tension parallel to the surface. The downward force of the ball is resisted by opposing forces within the metal. These opposing forces are compression as long as the load is maintained. Now the ball is removed. An elastic recovery or spring back occurs, forcing the indentation of the ball from its original depth to a more shallow indentation. This stress reversal causes compressive residual stresses to develop parallel to the surface of the dome-shaped depression. Now, suppose a large number of balls are pressed into the surface of the metal, covering the entire surface with indentations. A thin, compressive residual stress layer is formed parallel to the entire surface. Each indentation acts like an inverted dome with corresponding residual stresses after the balls are removed. This is the process of shot peening, widely used to improve fatigue strength and resistance to stress corrosion cracking. This basic process of mechanically stretching the surface, then removing the applied load, is used in many other ways to induce compressive residual stresses into critical locations. Surface rolling, consisting of hardened steel rollers forced against rotating shafts, is commonly used to strengthen fillets and cylindrical surfaces on crankshafts, spindles, railway car axles, very large propeller shafts of ships, and similar parts. Critical holes, such as oil holes in highly stressed parts, can be strengthened by ballizing. This process involves pressing a hardened ball through a greased hole that is slightly smaller than the ball. The ball stretches the wall of the hole, which then contracts after the ball has passed through. Thus, compressive residual stresses are developed in the hole. This is the positive side of mechanical pre-stressing. Tensile applied loads result in compressive residual stresses when the load is removed, and compressive residual stresses can be beneficial. The negative side is the opposite of this principle, that compressive applied loads result in tensile residual stresses when the load is removed, and tensile residual stresses can be damaging. The chemical factors affecting residual stresses pertain primarily to metal removal and electroplating operations. Electroplating particularly can impart damaging tensile residual stresses into the metal surface. In order to combat this problem, the electroplating of hardened steel parts with chromium often requires that the steel parts first be shot peened to neutralize the tensile residual stresses inherent with chromium plating. Residual stresses in metals is not an easy concept to grasp. It takes considerable review and reflection to understand the principles of internal locked-in stresses that can cause distortion and fracture as easily as the more obvious applied stresses. Residual stresses may be dangerous or highly beneficial, depending on their pattern and magnitude. In summary, though, we should point out the few basic principles that will help guide you in your study of residual stress. The most significant types of residual stress are caused by thermal, metallurgical, and mechanical factors. Thermal residual stresses are induced because the metal that cools last is in residual tension. Metallurgical residual stresses are induced because the steel that hardens last is in residual compression. Mechanical residual stresses are induced because tensile yielding under an applied load results in compressive residual stresses when the load is released. The opposite is also true of mechanical residual stresses. Compressive yielding under an applied load results in tensile residual stresses when the load is released.